Hey guys, today we're going to be covering optimization, related rates, linear approximation, and exponential growth and decay. And these are 4 of the AB topics we learned last semester. So we're going to start off with exponential growth and decay. So you might remember exponential decay from IM2 as well as Calc AB. And these are the 2 most important formulas to always know and take into account for. So this is exponential decay, this is exponential growth. So this one is, they are essentially the same thing. Pretty much the only difference is with this one, K is the rate constant, and with this one, this is the growth rate. For R is the growth rate. Okay, so now we're going to start off with an exponential decay problem. A new element, ferrarium, decays at a constant rate and was discovered in 2106. The scientists found the element to be extremely unstable, with the original amount quartering in just 0.35 hours. Given that the sample originally has a mass of 400 grams, find A, the formula of the amount remaining after T days, B, this amount of sample remaining after 29 days, and C, the number of minutes it takes for the sample to have a remaining mass of 2.7 grams. So we're going to start with part A, and basically we're going to use the information in the problem to solve for the equation. So we know that the original amount quarters in 0.35 hours, so we can use that and we can plug that in. So 400 divided by 4 is 100. That's equal to 400, which is the initial amount, times e to the r times t power, and t is 0.35. So we're going to do some algebra, and we're going to solve for r, and we get that r is negative 3.961. So now we're going to plug this into the equation. However, what most people might do is that they might leave this as this equation, but this equation is for when t is equal to hours, and according to the problem, they want the formula for when t equals days. So you have to be careful with this type of stuff, and you have to, in this case, divide by 24, and then you will get your answer there. Okay, so part B asks for the amount of sample remaining after 29 days. So all you have to do is plug in 29 for t into this equation that you solve for in part A, and then you'll get 3.342 grams. Next problem. So this asks for the number of minutes it takes for the sample to have a remaining mass of 2.7 grams. So we're going to plug in 2.7 as the final amount. And since we don't know t, we're going to solve for t. And then we get that t is equal to 30.292 days. So it asks for minutes. So again, you want to be careful with these unit conversions. So you want to multiply by 24 and 60 to get the number of minutes it takes, which is going to be 43,620.766 minutes. Okay, so next problem. To celebrate the upcoming 1000th anniversary of the disappearance of the bubonic plague has made a comeback, and since then has started an epidemic in CCA. The number of people infected at any time increases at a rate proportional to the number of people infected at that time. If 7 people were infected when the disease first came back, and this number tripled in just 2 days, when will 100 individuals be infected? So we know these 2 coordinates, which are time, comma, population infected, because of this last sentence right here. So at time equals 0, 7 people were infected, and at t equals 2, then this number right here tripled, so 2 comma 21, as shown here. So now that we know these 2 coordinates, we can plug that into the growth equation, exponential growth equation. So p equals c times e to the kt. So 21 equals 7, because that's when time equals 0, and that's their initial, times e to the 2k. So we solve for k, and we get the rate constant. So now we put the rate constant into the equation, and now we just set the equation equal to 100. And after we solve, we get t equals 4.844 days. So something important to keep in mind for exponential growth is that the question always has to state this sentence right here. The number of people infected at any time increase at a rate proportional to the number of people infected at that time, because that is what signifies exponential growth. The next topic I will be talking about is linear approximation. So linear approximation is using a known value to approximate an unknown. So this is just a little sketch of a graph I did, and this is just a random graph, so don't find the equation or anything. But basically, you are given a known value, and then you can't evaluate another value, so that is very close to this known value. So you use the tangent line at that known value to approximate what the unknown is. So here's an example problem. Approximate the fifth root of 32.2. So this equation is going to be f of x equals the fifth root of x. So the derivative of this is going to be 1/5 x to the negative 4 over 5. So we know that the fifth root of 32 is 2. So we can solve for the slope at x equals 32 of this equation. So then we plug in x equals 32 and we get 1/80. So now we can write the tangent line for when x equals 32. And that's just using the y value, the slope, and the x value. Now by plugging in x equals 32.2, we get this equation. And then we can just solve for y, and then we get this number at the end. The next topic we are doing is related rates. So for related rates, you always want to keep in mind the volume and area formulas because they will come in handy. So the first problem is this. A water tank is kept in Mr. Farrar's classroom to house the freshmen. It is built in the shape of an inverted cone with a radius of 2 meters and a height of 4 meters. A senior decided it would be funny to cut a small hole into the side of the tank. So now the water level decreases at a rate of 8/9 pi meters per minute. Find the rate at which water leaks out of the tank when the water is 3 meters deep. So we're going to start with doing part A. So something helpful I always do is I like to sketch the problem, so especially if it's related rates. So this is an inverted cone that I just sketched out, and then the height is 4 meters, and then has a radius of 2 meters. And then we want to find when the height is 3 meters, or the water level. So dH dt is equal to negative 8/9 pi because it decreases at a rate of 8/9 pi. Many students will forget the negative, and that will obviously affect your answer. We want to find when the change in volume. So now this is when volume areas come in handy. So the volume of a cone is 1/3 pi r squared h. So then we know the radius is 2, height is 4, so we can use this proportional ratio, and then we can solve for when r in terms of h. So r is equal to half h in this case. So now we can plug in half h for r into the equation, and this is so that we can do the derivative later on and just do it in terms of one x instead of an x and a y, or in this case an h and a r. So now we do the derivative, and don't forget the dH dt, and then you plug in the values that you know, which are the h, the d, and the dH dt. So you can solve for dV dt, and once you simplify, you get negative 2 meters cubed per minute. So that is, and don't forget the units, that's something that is extremely important in related rates. So part B is not knowing there's a hole in the tank. A sophomore pours water into the tank at a rate of 4 meters cubed per minute. Determine the rate at which the water level rises or falls when the water level is 3 meters high. So this is part B. So we're going to start off with we know that dV dt this time is 4 meters cubed per minute. So now we do the same proportional ratio, and then we essentially the same thing as this part. And then we get dV dt is equal to pi over 4 h squared dH dt. So same as this. And then now we know dV dt, so we're going to plug in dV dt and h. So we're going to solve for dH dt. So dH dt in this case is 16/9 pi meters per minute. but this is just the rate at which the water level rises, and we have to take into account the rate at which the water level falls, as given by this number in part A. So this is something that many students commonly forget about, and that is the rate at which the water level falls. So we have to subtract that from this number that we calculated, and we get 8/9 pi meters per minute. And again, don't forget the units. The last part I will be talking about today is optimization. So we're going to do one of the problems from the worksheet. Mr. Shea and Mr. Knudsen are boxing blocks of ferrarium for the calc students' post-final snack. And this time ferrarium is not radioactive. Each block of ferrarium must be 16 centimeters cubed. They decide to make a 4-sided box with a square base. Length of each side of the square is x, and this base is made of concrete, which is $3 per centimeter squared, and the sides with height h are made of wet paper towel, which is $1 per centimeter squared, and the lids are made of air for easy access to the contents. And in this context, air is 50 cents per centimeter squared. Determine the cost of the cheapest box. So what I like to do with optimization problems is I like to draw a picture. So this is the picture that I drew, and it's really simple. It's just a box, and then the two sides of the base are x, and then the height of the box is h. So we want to find the minimal cost of this box. So two equations that are very handy are volume and surface area for optimization specifically, and for this problem. So surface area of a box like this is going to be 2x squared plus 4xh. And then volume is x squared times h. So then we know that the volume should be 16 centimeters cubed. So I plugged in 16 for v, and then I solved for h in terms of x. So that will come in useful later on. So now for the cost function, I use the guidelines of the surface area and then the surface area function, and then I plugged in the costs of everything. So 3x squared, that's the concrete. Half x squared, that's the air. 4xh, that's the paper towel which is $1, and with the height h. And then now I plugged in 16 over x squared for h, like I solved over here, so that we only have one variable in this equation. So then I simplified. Okay, so now that's simplified, I did the derivative of the cost because it's just an x. So c prime of x is equal to 7x minus 64 over x squared. This is just basic derivatives. And then I set that equal to 0 to find the relative minimum. So when you set that equal to 0, you multiply by x squared, and then you solve for x, and then you get x is equal to 2.091 roughly. So so after this, you need to justify why there's a relative minimum at x equals 2.091, because you will lose points if you don't do so. And so you're going to say that c prime of 2.091 is equal to 0, and c double prime is greater than 0. So according to the second derivative test, there's a relative minimum at x equals 2.091. So now some people would just leave it as x equals 2.091 and just box their answer, but the question asks for determine the cost of the cheapest box. So you want to read the question really carefully. So here I just plugged in 2.091 for x into this equation right here, and I solved and I got $45.91. So that's how you do optimization. And basically for optimization, you want to understand what the problem's asking for. Then you want to come up with an equation for the scenario, and then find f prime and solve from there. So thank you guys so much for watching, and I hope this video was helpful.